Hi everyone, my name is Chris and I am a second year aerospace engineer.
Hi, my name is Cassandra and I'm a third year chemical engineering student.
My name is Andrade. I'm an alumni from Mr. Davis with a degree in mechanical engineering.
Hi, I'm Sri, and I'm a second year student majoring in mechanical and aerospace engineering.
And we are all representing the Coils team under ADCS for the Real mission, which is UC Davis's first undergraduate-led CubeSat mission. For our presentation, we will be going over the mathematical modeling, prototyping, and verification testing for our Magnetorquer components of our 2U CubeSat. So a brief overview of what we'll be talking about. First, we will talk about our system requirements and what requirements have to be met in order for our CubeSat to be functional in space. Then we will talk about our configuration of an air core and torque rod, followed by the optimization of the torque rod and the air core. Then we will talk about the manufacturing of our coil winder and testing procedures we took to test our functionality of our Magnetorquers. And now Cassandra will talk to you about system requirements.
For our system requirements, we have broken it down to control and constraints. For control requirements, we have a minimum magnetic moment of 0.0159 amp meters squared, and this comes from us doing calculations on the minimum disturbance torques that we will be experiencing during orbit. But we are optimizing our coils to have a 0.21 amp meters squared, which is just based on research of industry standards and us ensuring that we do meet that threshold. For attitude control accuracy, we want to have our CubeSat point in our desired direction within plus or minus 5 degrees, a detumble time of 0.5 degrees per second within 72 hours, and desaturate our reaction wheels within 12 hours. Our constraints come from our other systems of relop. From structures, we do have a constraint of a maximum dimensions of 80 by 80 by 25 millimeters. From electrical, we also have a constraint of no more than 2 watts when all of our Magnetorquers are turned on, and we have a mass constraint of 320 grams. Our team designed our configuration to be the following. We will have one air core, which is the wire that's wrapped around the structure, and 2 rods that are integrated within our structure. Both types of Magnetorquers are used to have a more compact structure, which was one of the criteria that we wanted to meet as a team. For dimensions for the air core, it will be 78 by 78 by 25 millimeters with one layer of 66 turns, running at 0.6 amps, and will be controlling the Z-axis of our CubeSat. For the X and Y axis control, we will have our rods, which are 71 millimeters in length and 6 millimeters in diameter, all having 3 layers each with 134 turns per layer and running at 0.4 amps. We also designed our configuration to be easy to manufacture since we are making it in-house, and we try to minimize as much space as possible. And now Andre will be going over our optimization.
The optimization process for the torque rods was particularly challenging, as it is a problem with 3 degrees of freedom. The goal is to maximize the magnetic moment being produced by the rods in order to satisfy our mission requirements, while keeping both the power consumption, mass, and volume occupied minimized. Assuming voltage to be a fixed value, the independent variables when designing the Magnetorquers were the shape of the rods, which corresponds to the ratio between length and radius, the number of the turns of wire, which varies the resistance of the coil, and the current being fed to the system. The only physical limitation for the current was the wire diameter, as it limits conductivity of the system. The main equation for optimizing the rods is the magnetic moment equation, as it describes how the moment is affected by the electrical components of the rods, as well as the material's shape and properties. When varying electrical parameters such as the current, the resistance of the wire, the first few terms of the equation are affected, whereas the last terms are affected by the properties of the rod itself, such as magnetic permeability, coercivity, demagnetization factor, etc. Note that those material-dependent parameters are not relevant on the equation for the air core case, since it doesn't utilize a ferromagnetic core. Another note is that the rod shape affects the magnetic moment with a logarithmic relationship, whereas the current has a linear relationship with the moment, as will be shown further in the presentation. The equations describing the electrical parameters are shown on the right-hand side, as derived from Ohm's law and the definition of electrical power. Those are the main relationships used to optimize the electrical components of the coils. During the optimization, the voltage was kept constant as it depends on external factors during the mission. The current, on the other hand, is controlled by pulse width modulation, meaning it's kept around a constant value by applying a voltage to the system and shutting it off whenever it exceeds that value, repeating the process with feedback loops. Moreover, as shown in the magnetic moment equation, to produce a given value of magnetic moment, a larger current would require less turns on the coil, and those values are chosen with respect to each other. And finally, it is important to keep in mind that manufacturing has its own limitations on the design of the rods, as a high number of turns and a small radius can make manufacturing significantly more challenging. Here, as previously discussed, the rod shape affects the demagnetization factor on a logarithmic scale, hence the exponential growth in magnetic moment. The current, on the other hand, is directly proportional to the moment and shows the linear growth relationship on the surface plot on the left-hand side. When turns are added to the system, the resistance is increased. However, it also decreases the current needed to produce the target magnetic moment, and therefore, it reduces the power consumption, which is proportional to the current squared. Another limitation for the current produced is the wire diameter, as each gauge has a limit as to how much current it can conduct. Now Chris is going to go over the optimization process.
A brief overview of our optimization process. We first began by maximizing the core shape by fitting the length of the rod inside the inner area of the air core, followed by decreasing the radius until a high core shape is achieved. Then we choose a wire gauge that provides the torque rod with a flexible operative region, which gives us a large range of current values to work with, since certain gauges can only run at a specific current for a prolonged period of time before burning out. After the gauge is chosen, we then choose a reasonable number of turns and required current value to achieve minimum dipole requirements. And finally, we check to see if our power and space requirements are met. So a brief overview of our MATLAB code we used. Here is a flowchart explaining how our optimization process works. We first determine our core shape and then check to see if the demagnetization factor is low and the geometric parameter of the rod is high. We then choose a wire gauge and then use an array of current values to calculate the number of turns required to achieve 0.2 dipole. We then plot a graph of current versus turns to see a wide scope of values. Once we choose a current value from this plot, we then calculate power consumption of the rod and plot a graph of power versus turns to see those values as well. Finally, we check if our power consumption is under 1 watt and if our number of turns is feasible and fits within the air core, then all of our system requirements are met and we have successfully optimized our torque rods. Now, Cassandra will explain to you how our air core is optimized.
For our air core optimization, we based it off of what results we get from our rod optimization, just so we could work around those dimensions. So this is a high overview on how our MATLAB code works, which is very customizable for anyone who is trying to make an air core structure. So we first define our variables to have a maximum outer side length, which mainly come from constraints from our structures team, thickness, which is also defined since it depends on the material that we will be using for the structure, as well as the total height and the clearance between the edge of the PCB and the coil structure, which comes from the mounting technique that we will be using. From there, we will have our inputs, so any desired power consumption that you have, voltage that's available for your CubeSat, and the wire gauge and inner side length, which come from the opposition of the rods. And from there, we run our code and it will give us an output of magnetic moment, number of layers, number of turns per layer, and the current. Note that we optimize this process to output number of complete layers, just so manufacturing is easy and we don't end our winding in the middle of the structure. And now Sri will be going over our manufacturing.
The manufacturing team has done multiple projects for this year, and one of the projects we worked on was the coil winder. So initially, when we tried to wind the coils, we winded them by hand. So this led to multiple problems, such as we had to count the number of turns using a clicker or some other source. And also we had the problem of wires getting intertwined with each other. So the coil winder would provide us a solution to these two problems. So the coil winder can define the number of turns and wind them accordingly without the wires getting intertwined. So the coil winder, most parts of the coil winder, as you can see in the pictures next to you, are made of 3D printer. Like we 3D printed them in PLA plastic. So what exactly the coil winder does and how it works? So the coil winder consists of two stepper motors and two drivers, each controlling the coil and the other controlling the spool. So as the coil structure starts rotating, the spool winds the wire along the coil so that we could get a neat and quality coils produced at the end of winding session. Since we had manufactured Magnetorquer coils, now we needed to test them. So the goal of a testing experiment is that to get accurate magnetic moment values and check if the magnetic moment values produced in the experiment are precise and accurate enough to the ones we got to the optimization. So in this experiment, we collect data from a magnetometer, which gives us the magnetic field. We use this magnetic field as an input into the MATLAB code that we wrote, and that would give us magnetic moment produced by the Magnetorquer coil at that point. So if you take a look at the test setup, there's an octagon base for the structure. So this allows us to get multiple points in the 3D space and also keeps the entire structure reduced in size. Moreover, you can see that the Magnetorquer coil setup also has the entire magnetic field to be accurate, because the magnetometer will remain stable throughout the entire testing process. Currently, we are still doing the testing and we are awaiting our test results. So once we would get the test results, we would proceed forward to our future works. So currently for our future works, so we currently are still manufacturing more prototypes, and once we are done with all our prototypes, we would give them off for testing with the PCBs for the electrical team and for controls and system teams to test for their pre-dot control. Moreover, since these are only the prototypes, we are yet to design and manufacture the final flight Magnetorquer coil, and also decide the space gate material that we would be 3D printing it in. Also, another project that we are working currently is to create a guide for universities to follow our methods. So the reason we are creating a guide is not just for other universities, but for our own club members and other companies who want to keep updated with our stuff, and so that any incoming students could know what we've done. And it also helps us keep updated with also other teams and other outside vendors and companies. Thank you everyone for listening to us, and we thank CDW for providing us such a wonderful opportunity to present, and we hope everyone stays safe and healthy. Thank you.